Hello, my friends. I'm Pittsburgh Pat, and I'm here with Gary Lionotto, my good friend. How are you today?
I am well.
That's great.
I'm well.
We always talk about some interesting stuff. We're going to talk about something interesting today. What are we going to talk about today?
Well, I want to talk about the black hole nature of the universe.
The black hole nature of the universe.
And it's interesting. The universe is a black hole. And right now, people don't believe that's the case. They play around with it, but they don't believe it. And the reason they don't believe it is the current paradigm for how black holes work doesn't really allow for it. But if you really take the same formulations and interpret them literally versus they say, well, they play around with it. They tinker with the explanation. But if you take the actual general relativity formulas, which we're not going to get into because it's a little bit beyond the level of this interview. But the thing is...
it's in your books. Gary's written 2 books, by the way, which we'll link below, and you can buy off his website.
Yeah, Black Holes, the New Paradigm is the one that really describes this.
Mm-hmm.
But if you actually look at it, we're a black hole. Now, the thing is, when you think about it, at the beginning of the universe, the Big Bang, it was a tiny, tiny universe. It was what they call Planck's radius, which is this phenomenally small area. The thing is, black holes are formed when mass gets to a critical density. When you get to that critical density, you curve space-time to the point where it actually makes a totally spherical curve. And when you hit that critical mass, it becomes a black hole. And we've accomplished this. They've accomplished this in stars. As a matter of fact, in the center of galaxies, you have these supermassive black holes.
Yeah, I've read about that. So the traditional idea of a black hole is there's this gigantic star that has such great mass that it collapses in on itself to a point where...
Presto, the light can no longer escape, and at the centerpiece... And what you have is curvature of space-time.
So the gravity is so strong that it actually warps space-time. That's what you're saying.
Exactly.
Okay.
Exactly. So
you're saying that... Now, I'm talking about this on a stellar level, but you're talking about this on a universal level.
On a universal level, because you think about it, they have finessed around the idea that the universe was incredibly dense at the Big Bang.
Right.
And it was contained in a very tiny area. So if you had all this energy and mass in a tiny area, the natural curvature, in other words, of that space-time, has to be a black hole. They know that. They know that the formulas call for a universe to be a black hole. But they say it can't be because a black hole is supposed to be a death knell of mass. It's like a junk heap where everything enters into.
Mm-hmm.
But in a certain sense, they're right for a black hole within our universe. But I always assumed that it was a black hole because what makes it a universe? In other words, what makes all of that goes on in the experiences that we have and every other matter and energy has in this universe, what makes it a universe? In other words, what makes it separate from the rest of infinity, the infinite everything?
Well, the last time we talked, you said there were 2 things that make a universe, right? One is like the laws that govern that universe, basically, right? Like the...
Well, I said basically the 2 things were you have to have existence.
Right.
And then you have to have observation of that existence.
Okay.
Now, the thing is, that existence is what makes it a universe. The thing is, we have...
So if it's just a black hole just sitting there, there's no universe. Or there is, but it's a really tiny, dense universe.
Exactly.
Now, the event that causes the Big Bang has expanded to the point where 13.78 billion years later, this is what we've got. Right.
That's what we have.
Okay. But all of that mass, everything that we can observe, everything in and beyond that even, was in that point.
Exactly.
That Planck length.
Everything, the initial seed for this universe was in this incredibly small. And they know, there's a reason they know that.
And that was a black hole at the time. Well, why is it a black hole still?
Well, I'm going to digress a little bit. I'm going to show you why they know what the Big Bang was.
Okay.
They know it because there's there's the two factors that I said to make it a universe. Number one is existence, and number two, the ability to observe that existence. Well, existence, what made it an existence was making it a contained entity. And to make it a contained entity was the curvature of space-time into a black hole at Planck's radius. Well, ironically, and then the way it observed its first event, which is what happened at the Big Bang. The Big Bang basically is the first event of the universe. The way to observe that first event was the first waveform. And the first waveform was also a Planck's radius. So in other words, at that location, there's that unique location. And here's what happens. What happens is...
Now, we've talked about waveforms before, but just so that if anybody's new to this particular discussion, a waveform is...
A waveform is you have different kinds of waveforms. You have waveforms of sound, and we're familiar with that. But when you look at the fundamental constituents of the universe, you have waveforms that are made by light, and light is basically just a waveform, and different lengths. A long waveform is a low energy light. A short waveform is a high energy light. For instance, a real long waveform would be like radio waves. And then if you get into very short, you get into
X-rays.
You get visible is this really tiny part. If you have a spectrum like this, the visible light part of the spectrum that we see is just here. And then the lower end, the long waves, you have infrared and then ultraviolet. And then you get up into X-rays, and the ultimate is gamma rays, which are very, very high energy wave.
So, but it all started with one waveform right as the Big Bang happens.
Big Bang. And they know the Big Bang's radius because digress again, matter also has waveforms. There was Louis de Broglie discovered that matter travels in waveforms. Now, what happens is we have containment of the universe. And the containment of the universe is general relativity. Gravity's containment of the universe makes it a universe.
Okay.
So at the Big Bang, you had the containment, which was the universe became this tiny, tiny, tiny black hole is what made it. But then you also had the first waveforms. Now, the thing is, for a black hole, the more mass you have, the larger the radius.
Okay, that makes sense.
If we made the Earth a black hole, if you crushed it into the density to make a black hole, it'd be 0.88 centimeters.
Okay.
It'd be this big.
Gotcha. Like a pea.
Exactly. But if you made the sun a black hole, it'd be 3 kilometers.
Okay.
So it's just about around 2 miles.
And that's a factor of its mass.
Because what happens is you increase the mass, the radius of the black hole increases proportionally.
There's only so close these particles can get together.
Exactly.
There's like a limit.
It's kind
is that the Planck limit as well?
Is that not in this case.
That's a different limit.
It's a Schwarzschild limit.
Schwarzschild limit.
Yeah, it's named after Carl Schwarzschild, who followed Einstein.
That's where the Schwarzschild radius comes from.
Well,
that's what we're talking about.
The strange thing about black holes is this: if you take the moon and put another moon and collect it together without making it any more dense, just 2 moons, and you say, okay, the radius will go from the current radius of the moon to, does it double? No, the radius goes up. You're doubling the volume, but you're spreading that volume over the surface of the moon. So your radius goes to actually the cube root of 2. In other words, the radius doesn't double.
That's
but
geometry.
It goes to the cube root of 2. It's just simple geometry. You're taking the cube root of the volume of stuff.
I can almost get my mind around that. Okay.
So it goes cube root of 2. So it goes up like 28%. So you collect all the rest of the second moon and gather. Matter of fact, I have an animation that shows this, and it gathers it together, and the radius goes up like 28%, which is a cube root of 2.
Okay.
So anyway, what happens? That's what happens to matter. But when you double the mass of a black hole, its event horizon, and that's how they measure the black hole. That's the point where light can no longer escape. The event horizon doubles. So
the radius of the event horizon.
The radius of the event horizon.
Okay, thank you.
Even though the critical density becomes less. In other words, to make the Earth a black hole, it's 0.88 centimeters. You're taking this 10 to the 26 kilograms and crushing it into that site.
Right.
But in the sun's case, it doesn't take nearly that kind of density to create a black hole.
Okay.
So what happens is you get progressively less. Well, the Big Bang, you needed 10 to the 96 kilograms per cubic meter to get it to make it a black hole.
So you're saying black holes are not uniformly dense?
No, the critical density to make the black hole.
There's a critical density to make a black hole, but some black holes are denser than others.
Exactly, and that's one of the reasons why the Earth
thought
will
of
never be a black hole. But really large stars can get to that critical density.
Because there's just not enough mass to make a black hole.
There's not enough mass to make a black hole.
Or with the sun, right?
I mean, theoretically, if something crushed it to that level,
Yeah.
there's no force that we know that can crush it.
But the sun's not large enough either, or
It's
massive
not- it's
enough.
not massive
enough. It's a difference. It's actually called a dwarf star, even though it's a medium. It's considered like a medium size on the main sequence if you plot them out. But yeah, so it's these really big, massive stars that end up being black holes.
Exactly.
They collapse.
So what happens is that's one of the characteristics. Now, so we come back to the Big Bang. You have two characteristics to make a universe. One is the existence, and existence it means that you're separating it from the infinite possibilities of everything.
Gotcha.
Of everything beyond anything we can even conceive of.
So in some kind of theoretical existence, there are innumerable possibilities. But for whatever reason, one happens, and then that's when existence comes into being.
So you must curve it into a space that makes it a black hole. And so basically you create the unit one out of infinity. And what I mean by the unit one, the mathematics of one.
Okay.
The idea, by saying we have a universe, we have identified something separate from every other possibility.
Okay.
It's our universe, but it's a universe.
But it becomes measurable at that point.
It becomes it's measurable to itself.
Right.
And so the number one, that's existence. Existence is the containment of gravity through general relativity.
Okay.
Now, then the other aspect of existence is observation of that existence. Well, the observation of that existence comes from the first waveform. What happens is the Big Bang starts from this initial center point, and it goes out one Planck radius, and it looks back on what it just created. So it has that observation of itself. And then the second instant is another Planck radius increase, and it goes back out and looks inward. Now the surface area of that black hole, because we're talking about this event horizon, has gone from 1, and it's a square, so it's, you have two radiuses. It goes to a square.
Gotcha.
4.
Gotcha.
So anyway, so that's what's happened to it. So the thing is, you now have the two characteristics to make it a universe: existence and the observation.
So it goes from being a pea to being like a ping pong ball, and then from a ping pong ball to a tennis ball, and then a basketball, and it just gets bigger.
Absolutely, and it gets
Okay.
bigger.
Gotcha.
So the thing is, we know that the density of the universe was so incredible, but they don't say that the universe was a black hole. And
What did they say the universe was? Or did they have
well,
an
they just say
explanation?
I've not heard a credible explanation for it. When it's expanding, it doesn't make it it avoids the general relativity formulations. But the general relativity formulations are absolute in any reference frame.
Right. So we've discussed this in a previous video. Your proposal says that there are, in your paradigm, there are no abrogations of general relativity. In inflation theory, there are. So, like for instance, and we talked about Guth and the inflation theory, which is a really interesting theory and very brilliant and accepted by some scientists, many scientists. But it assumes that somehow the universe expands at a greater rate than the speed of light. Is that right?
Yeah, but
Am I getting that right?
exactly.
Okay.
But at the same time, you don't have.
So if the speed of light is a barrier, whether or not it's variable, we talked about that in another video as well, it's still like the speed limit of the universe, whatever that speed happens to be at the time.
Well, you actually, I wasn't going to go into this, but you actually have phrased a question that sets me up on what is the speed of light.
Right.
Speed of light's it's number one, it's the growth rate of the universe, but it's the level of experience of the universe. It's the rate of experience. In other words, experience happens, from here to the end of the universe, but something measures that, or something calibrates that. How fast does that occur?
Okay.
Well, there is the speed of light, and I can give it to you. I can tell you exactly what the speed of light was in digital terms. In other words, I can give you the just numerical. I mean, we're talking about digital. We use the speed of light. We talk about miles per second, kilometers per second, whatever.
Right.
Those are human units.
Right. So that we can relate to them.
But let's just talk about it just digitally, going back to the old zeros and ones.
Okay.
So what is the speed of light? Well, the speed of light was basically the first instant, the first event was 1 unit of space, which is expanded 1 unit of space, and the observation in 1 unit of time. Well, we already talked about the first expansion. Well, the next moves out 1 more Planck radius.
Right.
Now the radius is 2.
Right.
Well, the surface area is a square. Areas are squares and volume is a cube. So the surface area is a square. So now the surface area is 4.
Okay. Well, you mean square, you mean mathematical square, not a...
Mathematical square.
Yeah,
No,
it's a
spherical.
Right, I just want to clarify that.
So what happens now, you have a surface area of 4. Well, the thing is, the velocity of light is the change in radius versus the change in the surface area, which is the time. Time is a surface experience because you experience it because the surface is the present moment. So the surface area is the event horizon, actually, in a black hole. So the present moment, you've expanded from a surface area of 1 to a surface area of 3.
Oh, I see what you're saying. Okay, gotcha. So as that expands, we are being carried along with that expansion on the surface of this event horizon, and that's our now. That's our experience. If we were able to, we could look back along that radius. That would be the past.
Exactly. But no, we get to the velocity of light. The velocity of experience. The surface area is the total experience of the universe in its whole history. But the ongoing the change in experience is it's gone from 1 to a total experience from a surface area of 1 to a surface area of 4. So now the whole experience of the universe is 4, but you've only changed 3. In other words, your surface area in the first instant was 1. Now you're 4, and one of those 4 was the first experience. In other words, the Big Bang itself. So now you've had a change of 3.
Just because of the
It's
geometry of the sphere.
the delta of 3. You've had a change in the surface area. It's 3. It's now a surface area of 4. So what the change in the radius is 1 because you've gone up 1 Planck unit.
Okay.
And the surface area is now surface area. The change in surface area is 3.
Well, we're really talking about dimensions here, right?
Right. This
What
is
you're
just
talking about is
straight
like,
geometry.
when you're talking about like the radius, you're talking about a one-dimensional thing.
Right.
When you're talking about the surface of the sphere, now you're talking about a three-dimensional thing.
Exactly.
Okay.
Well, the thing is, what has happened, but the surface area is a square. So what happens is the change is the square root of the change. And the square root of the change is 3. So now the square root of the change is the square root of 3. So that the Big Bang, the velocity of light, which is the experience rate, was 1 over the square root of 1. Now the surface area is 4, and we've changed a 3, so the velocity of light goes from 1 over the square root of 1 to 1 over the square root of 3.
Okay.
And then the next expansion, it goes out to a radius of 3. When you square 3, you get
So the speed
9.
of light's increasing all the time.
It goes to 9. Well, then what happens then, the velocity of light has gone, we've changed from a surface area of 4 to 9, because we're now 3 squared, and that is a change of 5 units. So now the velocity of light is 1 over the square root of 9. And then it goes to 4, which is 16, and and the difference between 9 and 16 is 7. It goes to 1 over the square root of 7, then 1 over the square root of 9. For each unit, 1 over the square root of 11. It goes to these odd numbers.
Okay.
The square root of those numbers. Now that's the velocity. It's changing very rapidly from the Big Bang.
Yeah.
Well, now
Is it still changing?
it's still changing.
But it's changing slower,
But now
right?
it's changing slower because we have a radius where the radius of the universe is the velocity of light times the age of the universe, which is 1.3 times 10 to the 26 meters. So now we increase 1 Planck radius, but we're starting with 10 to the 26 meters. Now, and 10 to the 26 meters is Planck radius. Turn it back to the only units that are natural unit is a Planck radius.
Mm-hmm.
Meters is not a natural unit. Natural unit is Planck radius. Now there's 10 to the 60th, 60 zeros, Planck radius. So when you move out one more radius, and you get a 10 to the 60th new events forming each Planck radius move.
I see.
So now it's 1 over 10 to the 6th, the square root of 10 to the 60th, which is 10 to the 30th. And you end up with a velocity of light that is 1, and sorry about getting into the technical numbers, 1 over 10 to the 30th of what it was at the Big Bang.
So
that's how it's changed. It's actually regimented in the mathematics of simple geometry.
Right. So basically, at the beginning of the universe, there are a limited number of possibilities. But as the universe expands, since that surface area becomes so large, and the numbers that you were using become so great, there are so many opportunities for things to happen on the surface that it's a de facto increase in complexity is what you're basically talking about, and possibilities.
The universe increases these 1 10 to the 30th. It's an incremental 10 to the 30th. There's a reason for that. It's the harmonics of the surface area, the event horizon of the black hole.
And that's the Planck length?
It goes up 1 Planck length at a time.
And that has to do with basically an analogy maybe to sound?
Well, it's very similar because it's the harmonics of the surface area, the event horizon of the universe's black hole.
Does this have anything to do with
simple harmonics? It goes in intervals. Simple. Same thing with an atom. You have discrete energy levels for the electron's orbits around the atom.
Right.
Well, you basically have discrete energy levels, and they work in harmonics of Planck's length on the surface area of the universe's event horizon.
Is this in any way? I'm just taking a stab here. Is this in any way related to like the wavelength that we detect the cosmic background radiation at, or is that completely different?
Well, it's relevant that the wavelength increases, and that what the cosmic background radiation does is the wavelengths increased basically 1,100-fold from that time. So yes, but in this case we're kind of talking about wavelengths. Wavelengths are the key for communication of information in the universe.
Okay, gotcha.
And so it's whether it's the information, the surface area, the event horizon is the total information that's ever been generated by the universe, all experience, and I mean all experience in a quantum level.
Right.
And
zeros and ones.
Zeros and ones.
Collapse or not collapse.
But anyway, so we're really just trying to establish the universe as the black hole.
Okay.
And it's the black hole's absoluteness that makes the universe an absolute. It makes its existence absolute. It makes its end and its experience absolute in one sense, that it will happen and it's contained within the universe. Now, quantum mechanics determines what that experience is.
Okay.
Quantum mechanics says, well, we have so many events to create, but we can create them in all these different ways, because every Planck increase, we get 10 to the 60th events that get generated.
Right.
The question is where those events get generated and how they get generated.
Right.
are all part of the probabilistic nature of the universe.
Gotcha.
And that's what makes experience unique in all circumstances. Because
it's not absolute. That's probability.
And it takes us, but this model takes us away from some of the spurious theories that say
you don't have the same problems.
Every event creates a new universe.
Yeah, you don't have any of those problems
because the new universe needs that containment.
Right.
So anyway, the universe is contained. So we'll leave that go for now. Now the question is, what makes our experience in this universe what it is? And this is really, really interesting. When I first started looking at general relativity and how it works, we realized that gravity is so incredibly strong near a black hole that it curves light. and they proved it that was how they actually approved it. Was it Eddington, I think, who did his experiments?
Sir Arthur Eddington.
Sir Arthur Eddington back in 1919, I think it was. But there was an eclipse there, determined the light curved around the sun.
Mm-hmm.
Well, what happens is the curvature becomes extreme. Light curves around the Earth to a tiny, tiny degree. Good lights, but the light's very little affected by the gravity of the Earth. But
right.
If you get the gravitational density sufficient, the light will curve. And what's cool is light will orbit a black hole. Now it's a very tenuous orbit. It's very unstable. So usually it happens. Periodic. It happens, but it immediately dissolves afterwards.
Is that because the inflow of matter into the black hole, and black hole's accreting and it has more mass, and therefore it pulls in?
That's it. No, well, the tenuous orbit. Let's say there's no accretion of matter, but the tenuous orbits can go either way. I mean, it's just like it's like pushing a pencil that's very tenuous. You don't know if it's going to go one way or the other.
Okay.
If you're trying to balance a pencil, but it's like that. So, but anyway, some light will orbit a black hole.
Gotcha.
But where does it orbit? It orbits at 1.5 times the event horizon.
It doesn't orbit at the event horizon.
Not the event horizon.
1.5 times.
Because the event horizon is where light cannot escape.
Okay.
Because the gravity is so massive that what it does is it stretches light's wavelength to an infinite length.
Okay.
So it's in effect it's black. That's why they call it black. But light will orbit a black hole 1.5 times the event horizon.
See, that's interesting because I always thought that the black hole was black because that's where the surface of the black hole was, but it's not. It's where the light disappears, and the actual surface is below that area.
You could be below that 1.5 margin and shine a light, and you can see the light.
Right.
Now it's going to be redder than it was when it left the light.
Yeah.
But you would be able to see the light. But light orbits. Now let's say you're at that 1.5 margin.
Okay.
Let's say you were able to stand, which you can't because the pressures and the gravity is so massive. But let's say you were able to stand there with a spacesuit, and you have a red light on your back, and if the black hole's small enough, you could look straight ahead and see the red light on your back.
Right.
And so that means light's gone from your back, orbited around, and gone to your eye.
Sure.
So what happens is, I thought about this, and this is my thought experiment. I said, well, what happens, what do you see when you're at that level? When you're at that 1.5 margin? Well, you'll see your starscape up above you, which will be half your field of view, because anything below that straight orbit to you is coming from below that orbit, which means it's coming from the black hole, and they're coming from the direction of the black hole. So
right.
When you're at that 1.5 margin, the black hole looks completely flat. You don't see the curvature of the black hole from that vantage point. Black hole looks completely flat because you'll see. So your field of view will have black hole in the, below here and starscape above here. Now, if you come down below that,
it's like being at Kansas at night.
See, light orbits here, but below that, in the black holes here, light starts to curve inward.
Right.
So at that point, light's curving inward, and what does that mean for what's your field of view? What happens below that? What happens is a starscape starts to close up.
Right.
And so what
I've heard this.
What replaces that? Well, the black hole starts to roll up around you. It's really, really...
Like the black hole physically rolls around you? That doesn't make any sense.
Well, visually.
Yeah, visually. See, I've understood that like eventually like you'll see like a closing circle of light above you as you descend further into the black hole.
But when you get to light, though, it's a little bit different than we think of. It's not like sitting on a lake surface.
Right.
You sit on a really smooth lake, you get right at the lake level, in the water, and your eyes looking, everything's flat.
Okay.
And it looks like it's flat,
with
but
a
there's
diver's
still a little bit of curvature.
Sure.
In this case, the direction of light becomes the straight line. It actually becomes it because light travels at what they call the null geodesic. But anyway, it is whatever light indicates is straight because it is the fastest velocity possible. So what happens is you go down below that, level, the universe starts to fold up around you, to the point where you get to the actual event horizon, where light can no longer escape. The only access to the event horizon is directly vertical. You cannot get to the event horizon at an angle. You cannot go at an angle like this. You can only go directly into the event horizon.
Okay, and what happens?
All light's curving. Now, wherever the event horizon is, light can come from different areas of the universe. Whatever its final access to the event horizon is vertical. So what is the view from the event horizon?
Imagine it's blinding white light.
Well, that's true. That's the other aspect. We'll get to that in a little bit later. But what happens is the entire universe, the starscape, squeezes off to a single point.
Right.
I mean, literally a point. Now, normally, light comes to you in a plane. You know, it's a curved plane, but
Sure.
it comes to you in a plane.
Right.
It comes to you in a plane. But now, you've taken that plane and made it a single point. So what's replaced that? Well, the black hole's rolled up around you. Wherever you are at the event horizon, the black hole visually and in real sense is rolled up around you. So what's happened is that's what black holes do. They change dimensions. They've taken that dimension of space outside and they moved it inside, because you're looking at the black hole, you're looking inside, you're basically looking at inside the black hole. Now, it's black at this point, but it's still, you're looking at the black hole.
So it's not the surface of the black hole, it's the inside of the black hole.
Yeah, and there's a reason for this. Your infall rate, your mandatory infall rate is the velocity of light.
Okay.
Now the velocity of light goes down to zero, which is kind of a real interesting point. But there's a relative to the outer universe, velocity goes to zero. But it's interesting. There's something. I'm going to go to special relativity now rather than general relativity. Special relativity says if you're traveling very rapidly in a spaceship, let's say, what happens is there's something called the headlight effect. What happens is objects forward of you start to squeeze off to a smaller and smaller aperture. For instance, objects, let's say you're passing at this moment, you have light coming in from here. Well, by the time the light gets to you, the light's going to be coming, that light's a waveform, that light is going to come to you from an angle actually behind you. If you're going very, very high speed, the light ends up being angled towards you, or coming to your spaceship from behind. I'm talking about original angle of the light's 90 degrees.
Okay.
It's going to be viewed at some angle towards your rear.
Because you're
so the only
passing the point at which you would have.
Exactly. And it'll be what we call red shifted. The light will have lower energy.
That I understand.
Well, what happens is the effect is light is focused more and more to your front. So if you are, so what happens is they call the headlight effect.
So I'm not sure I get that. So if I'm traveling and there's a light that, if I'm traveling at say 70 miles an hour, it would intersect with my vehicle like at a right angle. But since I'm going near the speed of light, why wouldn't it just miss me?
Well, what happens is the light, that means that the waveform is going to be curved. Okay, you're moving forward.
So I'm curving space-time in my craft as I'm
the
moving
light
that fast.
does get to you. So when you're looking out there, the light does get to you. Now we're getting into some pretty complicated stuff.
Yeah,
special relativity.
Okay.
But let's just stay with it. Let's stay with the
Okay.
idea. You get the headlight effect.
Sure.
What happens is if you go the velocity of light, all you see is directly in front of you, and you can only, if you're going at the velocity of light, which you can't travel in a spaceship that fast, all you see is very, very bright directly in front of you.
Mm-hmm.
And what's happened is the behind you has rolled up towards your front. And the only place and so that's like the black hole, because what happens is what's behind you, you're moving away from it, so the light waves get stretched and stretched and stretched. So it's like black hole being rolled up around you. It's very similar to that kind of thing. Your light from the rear gets rolled up around you, and your front, you get a very, very intense light.
Okay.
On the event horizon of a black hole, that's what it's like. You have light coming from above, and it's very intense.
Yeah.
But the rest of the black holes are rolled up around you.
Gotcha.
So anyway,
I can
we don't want to take
deal with that.
But what we're really talking about here to explain the universe is we're going from the fact where you're talking about a black hole within this universe to where actually we are a universe.
Right. So
Universe
totally
as a
different
black hole.
idea.
Well, not totally different. It connects. And here's the connection. Black holes move a dimension of space from outside to in.
Outside what?
Outside the event horizon, good question, to inside the event horizon.
Okay.
So we exist on the surface of a black hole.
So you're saying that
on the
the
event
third
horizon.
dimension's not there. It's two dimensions at that point.
Well, outside. What's happened is we've moved a dimension from outside. That's what black holes do. When you move at the velocity of light, you're switching dimensions. It's a dimension shifting experience. We're moving dimensions. And we're moving space. Now, the thing is, we still have 4 dimensions.
So you said, well, we're inside the black hole. Everything looks like it's two-dimensional, right? Looks like it's flat. Is that because of that dimensional shift?
No, that's not what I'm saying.
That's just a perception.
What I'm saying is this. We exist on the event horizon.
Okay.
But what we see is inside our universe's black hole.
Oh, I see.
What's happened is...
So that folding up effect is what we're looking at when we look at the night sky.
Exactly. We exist on the event horizon of a black hole. Now, we're not talking about a black hole within our universe where you have black rolled up around you.
Right.
We're on the surface area where you have the universe. Our universe is rolled up around us, our point on the surface of the event horizon of the black hole.
Does this have anything to do with the theories that the universe is shaped like a saddle? Does that have anything to do with that?
That's whether it's an open universe or a closed universe. It's a little different.
It's different.
A little different, but you're going the right way. But the thing is, if you look at it this way, how do we know that the universe is rolled up around us?
I don't know. Can we test for that?
There's a logic test. And here's the logic test. How do we know we added a dimension inside the universe? Well, probably the best example I have is this. We now have deep space views with Hubble telescope and other methods.
Okay.
We know of distant galaxies and we look into the distance. We're looking into the past. And what is the past? Well, and so we're looking at these galaxies but we can look at them down here, down there, everywhere we look around from wherever our telescope is located. We can see that we can see back 10, 11 billion, maybe even 12 billion years ago.
Okay.
Very close, getting pretty close to the Big Bang, or the cosmic. Yeah, exactly.
Yeah.
But let's say, where did all the galaxies we're looking at, or the cosmic background radiation itself, where did it come from?
Well, it's my understanding the cosmic background radiation is an echo of the Big Bang, so
It is.
that's as far back as we look, right?
Exactly. But they all came from the Big Bang. Everything we see comes from the Big Bang.
Sure.
So the Big Bang was a single point. It was this size.
Right.
It was this tiny.
Right.
Well, where's the Big Bang? Is it there? Because that galaxy came from the Big Bang.
Yeah, I've always wondered.
That galaxy over there came from the Big Bang.
Sure.
That galaxy over there, the one over there came from the Big Bang.
Right.
They all came from the Big Bang. So where's the Big Bang?
Right.
It's there. So the Big Bang is this ethereal shell that's moving away from us at the velocity of light. So we have Big Bang was a single point.
Right.
We took a dimension from outside the universe, rolled it into the universe, and made that Big Bang a surface area. It's a surface area. We've added a dimension to the surface area.
I'm not following. So yeah.
Okay, now the Big Bang is a point. Start off the point.
Okay, so that's one
When we
dimension.
see it, if we can see it,
Yeah.
we know its existence is a plane. It's a curved plane moving away from us.
Curved plane.
Curved plane.
So
plane,
two dimensions.
Plane sounds like it's 2 dimensions.
Okay.
Because it has two dimensions, and those 2 dimensions are you could draw squares in space. The squares, Big Bang's over there, Big Bang. But it's the furthest thing you have away from us that can be conceptually, mentally observed.
So we're somewhere inside a sphere looking out at the surface of a sphere.
And the edge of that sphere is the Big
the cosmic
Bang,
background radiation.
No, it's the Big Bang itself.
But we can only see as far
We
back.
can only see as
we
far-
only detect radiation as far back as
Exactly.
that.
But
beyond that, you're saying is the Big Bang.
is the Big Bang.
But there's no way for us to test for that.
The Big Bang, you can probably get earlier. Neutrinos probably originated before the cosmic. Probably came from some of the earlier experiences. Probably penetrated.
So if we got really good at detecting neutrinos, maybe someday possibly.
But you won't know the source. I don't think we'll ever be able to fine tune that. But anyway,
gotcha.
We know that conceptually, everything was created by the Big Bang.
Right.
And where's the Big Bang? It's all the way around. So we've added a dimension to that surface area that's moving away from us.
That makes sense.
All right, now, so what are we looking at when we look at those galaxies? Well, we're looking at objects that are moving away from us or whatever, or they could be stable, like looking across this room.
Yeah.
But everything you see is the past.
Yeah.
So what we're observing is the past. We're not observing the future. We're not observing the present. We're observing the past. As I said, one of the characteristics of it makes it a universe is to be able to observe yourself. Well, this is how the universe observes itself. It observes through light and any energy communication.
I see.
It observes itself.
So the pattern of that galaxy, which existed 10 billion years ago, that Hubble is picking up, is preserved in the light that has been emanated from that galaxy. Even though that galaxy, in real time, in our present time, doesn't exist anymore.
The second characteristic that makes it a universe is observation of itself. And,
so light
it observes on the current event horizon.
Yeah.
It observes events of the past. So what do we know the past. We know it's XYZ axis of Euclidean geometry.
Right.
And then it's also
and then time.
It's time because we're observing things in the past. It's how much time it took the light to get to us.
Right.
So how far in the past is it? Well, we can say it's in seconds, but seconds we're really referring to
distance.
Referring to distance, exactly. Like something can be
Parsec.
so many nanoseconds away from us, or we can sun's 8 light minutes away from us.
Right.
We can measure it in meters, but what we're doing is we're really converting time
and distance
into from speed of light into distance.
Right.
Or you can look at the nearest star, nearest stars or whatever. But then you see those galaxies are 10 billion years in our past.
Right.
So we're looking at the past. So our 3 dimensions of space and 1 dimension of time, because time is depth. It's like you have a sphere.
Right.
How far?
That's a great way to put it.
We're the center of the sphere, and how far away
are
those events? And whether we observe them or they're still in our past. So that's what we see.
Yes.
Well, the question is, but we're seeing the past.
Yeah.
But we're seeing the past in the present.
In our present, not its present.
Because where we are is we're in our present.
Right.
And so what does that mean? Okay, well, how do we see? What is the present? Well, there's a universal present in the universe. That's one thing that unifies everything. It unifies the physics of the universe is that we have a common radius from what? The Big Bang.
Right.
The Big Bang's the center of the universe. Right. Big Bang is that point. Now I say it's a spherical around us, but in reality, we've taken a dimension that was the center of the universe because everything's radiated from around the Big Bang. But wherever you are in the event horizon, because of that switch of dimensions, that whole universe, even though it's a center point and we're on the surface of a real sphere,
right?
We've actually taken that universe and rolled it up around us.
Right.
It's in the way it is, but it's more than just conceptually and visually. It's actual reality. Our reality is we are in the center of our universe.
So our present.
So ironic. The real center of the universe is the Big Bang.
Yeah.
But ironically, we're the center of where our universe. Wherever we are, we're the center of that universe.
But that universe is. I mean that our present is locked in time by the relative positions of everything else around us. I mean, it's the expansion. So any particular moment is a factor of where and how far the universe has expanded at any given moment. Exactly. Right? You can measure it in radius. You can talk about it in terms of time, but it's basically the same thing.
It's the same thing, and it's the nature of black holes, where you measure a black hole. the way they currently look at it, and I've adjusted this. If you fell into a black hole, theoretically you go to crush to a singularity in the center, and it takes so long to get there. So you have a black hole that's from outside is 30 light years across, or radius.
Yeah.
It takes 20 years to go from a 30-year. It takes 2/3 the time of what we would measure from outside to actually get into the central singularity. But
right, and that's not the same singularity as the electronic singularity.
I say that it's not the singularity.
That's
really
a structure of a black hole. That's the center of the black hole.
The center of the black hole really is the Big Bang. But the point is, my whole point is, the real way black holes work is you don't get through the event horizon.
Right.
That's the point of action.
That's where you stop.
But we're gonna stay away from that for the moment. We're trying to talk about this change of dimensions.
Right.
Okay, what happens is you observe everything around us. Because I said the key is the universe has to be able to observe itself. So how do you observe it? You observe it in the present. So in the present, we're observing the universe.
Where else can you
Well, light comes from that wall over there, hits your retina. There's an exchange. Observation is the exchange of mass and energy creates events. Creation of events. Events are created in the present. We live on the event horizon. We look at a black hole, it's where we can no longer observe events, it's called the event horizon. When we are the black hole, the event horizon is where all events are created.
So that's literally the meaning of event horizon, is that you can't see over the horizon, so you cannot see any more events beyond it.
That's where you can't see them. But in reality, it's the perfect word for what we live on.
Yeah.
We live where events are created.
Right.
And we live in the present.
And that's the present.
And we observe events of the past. They meet the retina, and you have a cascade of events.
So if you look down the singularity, is that the past or the future?
The singularity for our universe is the Big Bang.
So if I look up from the event horizon and I see that closing pattern of stars, that's the past.
It's the past.
If I look down into the singularity, that's
the
future?
You're looking down in the future. No, the singularity is everywhere.
Ah.
Remember, the singularities
The singularity is the black stuff around the star field. Because that's the interior of the black hole.
No. Okay, we're talking about... you have to separate. Are we talking about a black hole within our universe, or are we talking about being the universe black hole?
They're not the same thing.
The black hole makes containment of our universe. Black hole contains our experience.
Okay.
Makes everything interconnected.
The universal
law, second law of thermodynamics. Everything's interconnected in this our experience, which is our universe, which is our universal black hole. Okay, so now we're talking about our universal black hole. Originally we're talking about how black holes switch dimensions and how they do it, and we can do that by observing a black hole within our universe. Now we're talking about how being a black hole universe, what that switching of dimensions means. What that switching of dimensions means is this. You're observing objects. And observe objects, light goes to you, hits your retina. Retina has a electrochemical reaction. It exchanges mass and energy.
Right.
Then that gets sent by a continual cascade of change of mass and energy. Then it goes to the brain and finds the pattern that recognizes what that object is.
Okay.
And then you mentally have to respond to it. It's a cascade of tons of events just on any light hitting your retina.
Right.
Those are events, but those events are created as an exchange of mass and energy. Now, how is mass and energy exchanged? From the ultimate formula of all time.
E equals MC
E
squared.
equals MC
They're
squared.
interchangeable, right?
They're changed through E equals MC squared.
Right.
So, what is C squared? It's the velocity squared, right?
Yeah.
It's velocity of light squared, but so is unique velocity. So it's the velocity of light squared. Well, what is velocity of light? Well, it's distance over time. If you square it, it's distance over time times distance over time. So you have 2 dimensions of distance, 2 dimensions of time. So what is 2 dimensions of space? Distance would be space, and 2 dimensions of time. So what is the present? It's 2 dimensions of space and 2 dimensions of time.
And where's the third dimension?
Well, it's still 4 dimensions.
What?
It's 4 dimensions, right?
No.
2 of space
Yeah.
and 2 of time.
2 of time.
Two of time.
What do you mean 2 of time? How do you have 2 dimensions of time?
C squared.
I don't understand.
Well, I know we're not there yet. You will understand. We're observing.
Oh, they understand.
We're observing the past
Okay.
in the present. That's 2 times. Past observed in the present.
I see.
That's 2 times.
So you're saying, yeah, but that's just like semantics, right?
No.
Yeah. I mean, I'm looking at starlight, but the starlight has reached me. So that's in my present. It's in my present relativistic frame.
That's
time
right.
frame.
So you're combining the 2. You're combining the past and the present.
But it's just the present.
You're observing the past and the present.
I'm observing a reflection of the past, but the light is here now, so it's in my present.
It's not semantics because it's the exchange of mass. The present, what is the present? The present is the generation of events.
Yeah.
Events are generated.
In the present.
Are generated with C squared.
Okay.
And that's 2 dimensions of space and 2 dimensions of time. Remember, you're observing the past. When we think that what we live in is what we see and what we observe.
Yeah, the eternal now.
Yeah, but we're observing in the eternal now. But
Right.
the actual present is the creation of events. Now, so that's 2 dimensional space. Right, stay with me on this.
I'm trying.
2 dimensional space and 2 dimensional time. Now, well, what is the future? I'm going to carry this one more step. We took a dimension from outside the universe and put it in. The future is future radius of the black hole. We're
Right.
expanding
What
out.
we're expanding into,
We're expanding what we're expanding into.
or what we're going to be when it expands that far. That's the future.
That's right.
So you can't see the future because it hasn't happened yet.
The future is 1 dimension of space and 3 dimensions of time. The future exists now in our 1 dimension of space. What is the future? Well, you exist wherever you are on our surface of this universal black hole, wherever matter is, it ages. Future comes to you. You don't have to move to it. It comes. You can move, but it comes to you. The future comes to you. But the future is 1 dimension of space, because wherever you are, you age. And 3 dimensions of time. And we're not talking about semantics. We're talking about formulas and everything else relates to it. The future is 3 dimensions of time. What do you mean 3 dimensions of time?
Yeah, I have no concept of how that.
How does it even make sense? How does it even make sense?
I don't even know what that
Well, what
means.
is a time dimension? That's what you really come down to.
Yeah.
So we still have 4 dimensions. There are only 4 dimensions, and there's just exchange. You exchange for 3 dimensions of space inside the black hole and 1 dimension of time, which is depth. The surface of the black hole is you have 2 dimensions of space, 2 dimensions of time, because you're creating events. The future are events that haven't been created yet, but those events come to you through 3 times. Now let's show what those 3 times are. Well, the past only has 1 dimension of space or time. 1 dimension of time means that what affects the past? Only the past affects the past. So the only dimension that matters is events in the past affected the past.
Only the past affects the past.
You cannot affect the past in the present.
Can't change the past.
Can't change the past.
The past can change the past.
Past, you can't change it to us because we're in the present. And we can't, the past cannot change from our vantage point on the event horizon of the black hole. Now, in the event horizon of the black hole, the present is affected by events of the past. You change because of events you see. You change because you move. You said.
How about that?
You change your position or
Sure.
move whatever.
See something coming at you,
so
you dodge.
Whatever happens in the present is affected by events of the past.
Okay.
The energy of the past affects the present.
I buy that.
The future is affected by events of the past, events that are occurring now, and events that haven't occurred yet affect the future. There are 3 times that affect the future. And the future comes to you wherever you are on the surface of the black hole. Now, you can move on that surface of the black hole, but wherever you are, you're moving vertically outward to higher radiuses. Wherever you are on the surface of the black hole, your singular point of occupation on the surface of the black hole is unique to every piece of you. Is 1 location on the surface of the black hole.
So you don't move in sideways or up and
Yeah,
down.
you can.
You just move.
Well, you
just
don't
there.
move up and down on the surface of the black hole. The black hole horizon moves outward.
Right.
It just moves outward. We coast on the horizon of
Yeah.
the black hole.
Okay.
Now, the
So we're
forces
saying
and everything
one
else gives
dimension of
us.
space, though, your point.
Your
single
every point of your three-dimensional body exists on that same surface. It's the same distance from the being. Let's take another way to look at it.
Yeah.
If you look at where do we exist, we're established the Big Bang is the center of the universe. We exist at radius x at this, let's say at 12 noon.
Mm-hmm.
We exist at whatever x is, whatever that distance is from the Big Bang.
Okay.
Because that's what we've
That's
expanded
x.
velocity of light. You take
Got
the
it.
time, the age at
Yeah.
that moment
Okay.
to that point. Well, 1 second later,
X plus 1.
it's x plus 1 second times the velocity of light, which is easier, 300,000 kilometers per second. So we're 300,000 kilometers distant from that point that we were before.
Okay, I'll buy that.
So that event is in the past by 300,000 kilometers away.
Okay.
Now, we don't see that.
Right.
We don't see it's 300,000 kilometers. But it is. It's like this. You're traveling down the road in a car, and you're going, let's say, 60 miles an hour, which is 88 feet per second. And you're sitting there, and you have, Tara sitting next to you in the car, and you throw her a map. And it takes a half second to get from there to there. Well, the car's traveled 44 feet, but to you, it's just gone this little distance. So the thing is, though, let's say the roadway is the time that's gone by since, where real space has expanded during that period of time. In this case, you've gone 44 feet. So in reality, the map went way out here in this little curve to get to Tara, who's sitting next to you. But to you, it's just here to here. We coast on the event horizon of the black hole. We're coasting, and you don't. If you had no vibration, no windows, and anything else, you wouldn't. It would just be this distance. That the fact that the car is moving means nothing.
Right.
And that's where we are. We can't feel the expansion of the universe.
Yeah, it's our relative position.
Because our mass coasts with the momentum of the expansion.
Right.
So the thing is, you don't see that, you don't feel that.
Right.
So that's what's happening. That's what's happening in our experience. So we coast with the horizon. So we're always on the event horizon. It's mandatory. There's no option. So we're always, because that's where all matter exists.
Mm-hmm.
So the thing is, now what is the nature of that? So the past we're looking at. You're looking at that wall or whatever. That's
in the past.
Based on where we really exist now, it's 300,000 kilometers away, or more than that. How many seconds, or whatever fraction of a second it took to get here.
Okay.
That has moved into the past while we keep moving outward. Just like the roadway moves behind the car and moves away from you.
Okay.
So what we live 3 dimensions or 4 dimensions total. They just shift. And black holes shift them from outside to inside the black hole. Outside is the future because the black hole's expanding. Inside the past where we're moving away from it. And the present is where we are always because we're coasting with the mass of the universe. So the thing is, let's take a look at what that means. We can observe, we have 1 dimension of space in the past. And we can say, let's just talk about an experience. Let's say you had to get up for an appointment
Sure.
a week ago.
Sure.
And so I had the appointment, was 9 o'clock on, let's say, last Thursday, and I had to get up. So I had, at that time, I had a plan. I had to set the alarm the night before, so I had to go back further in the past. Or you can go back and forth mentally. No, we're not talking about actually physically going there because you exist in the present. But mentally, you can say you can go in the distant past or move forward from the past.
Yeah, I have a memory.
But you can you can assess the past. You can assess what you've done in the past, which is history and regret.
I can
and
look at
everything else.
I can look at my experience.
Exactly. Look at your experience.
So you're saying the universe can do that too?
Everything can do that.
Sure. Okay. Great.
It's
I
in
can buy
aging.
that.
That's part of aging.
What the past is.
That's what aging is. Matter does it through aging. It carries its past with its aging.
Nice.
So what happens is, that's what the past is. But the thing is, you can move back and forth in it. And the reason you can is because you can say, well, I moved from this, I set the alarm in this room and I woke up in the bed over here. There are different locations in space. Well, there's different locations in 3 dimensions of space with the past, when you observe the past.
Yeah.
Okay, so you can do that because they're odd dimensions. What I mean by that, you take the 3 dimension of space as a cube. In the single dimension of time, it's an odd dimension. You can move back and forward because when you cube a number, you maintain the sign. When you have a number to the first order, then you also maintain the sign. Well, the future, you can do the same thing in the future, except you're planning rather than assessing. You can say, well, I have to set the clock for this to get up for that appointment, and you can go backwards and forwards in planning where you want to be. Now, you're not there, but you're planning it.
Okay.
You're only at the event
Thinking about it, speculating. Sure.
But the present, you can do that because you have 3 dimensions of time, which is an odd number of dimensions, and you cube a number. It's always maintain a sign.
Mm-hmm.
You can go forward in the future. You can plan more distant future, less distant future. You can go say, you can plan your whatever it is. So the question becomes, the present is 2 dimensions of space and 2 dimensions of time.
Mm-hmm.
So when you look at that, what does that mean? Well, 2 dimensions of anything, you square time, you get a positive number. You square a -2, you get a
2 negatives make a positive.
You make a positive. You square the space, you get a positive.
Yeah.
Square the time, you get a positive. The present can only move forward because it's a square of space and time. So it only can move forward.
So you're talking about the arrow of time. You're talking about time
Arrow of
can only
time
move
is
forward.
established by that.
And that's because of pluses and minuses.
Exactly. Time can only move forward.
So that's a mathematical thing.
It is. The thing is, nothing can occur in this universe, including the planning and assessing and everything else we talked about, if it was not allowed for by the mathematics and the structure and the physics of the universe.
Gotcha.
Even our imaginings have to be allowed for.
Makes sense. Sure.
By actually the physics of the universe.
Yeah.
We think that it's outside of the physics. It's not. Everything we come
I'm
up
sure
with,
it's explained by
every
physics.
rationale, every reasoning, every dream, everything we have is a product of the physics. It was allowable by the physics of the universe. Otherwise, it couldn't occur.
Right. That makes sense.
Including all the esoteric stuff that we talk about.
Sure.
So the present is okay. You can watch. In our day, so many people, Keystone Cops. You can watch a movie going backwards, and it looks absurd. It's absurd. You can see and if you watch the movie going backwards, and you got younger while you're watching it, it's the same thing as watching it go forwards. That's what 2 negatives mean. If you make it 2 negatives, it's like, or glass breaking. We know the idea of a glass coming back together is absolutely absurd. We know that doesn't work.
Yeah, I've seen that in science books before.
But if you break a glass and you get younger while the glass breaks, it's the same thing as it going forward. I mean, in other words, if you see and you experience, if both the observation and the experience, because the present is experience.
Yeah.
The creation of events is experience. If you observe things going backwards and the experience goes backwards, it's the same thing as going forward.
So your mathematical formulas in your book explain all of this.
Well, this is just logic.
Oh, okay. Very good.
It's just logic. So the thing is, 2 negatives mean something forward. So space can only expand. It can't go backwards.
I believe that.
Okay. That also means that the universe cannot collapse on itself.
Okay, so
because the radius is the time it
took. So it's
took.
an open universe.
The universe expands at the exact velocity of light, and that velocity changes. And so it expands at the exact escape velocity, which is if you send a rocket ship up at the exact velocity with no excess to escape Earth, that's the escape velocity. The universe expands at the exact escape velocity. But it also means but it's in the mathematics, because the mathematics comes from the mathematics of black holes.
Gotcha.
Black holes, general relativity, the escape velocity is the event horizon always is the velocity of light. Anything falling into a black hole, the event horizon is always moving at the velocity of light.
So how do we test your theories? Like, is there any way to prove this in the observable universe? Is there any way, like,
Well, the connection, we had a conversation about the velocity of light.
Yes.
And we know how much the velocity. Well,
So
I
how
know
do
how
we?
much the velocity of light. I think I said,
You said
3 millimeters per second per year.
slower
I think
in
it's
the
I think
past.
it's 7.
Yeah.
It slows down 7 millimeters per second.
So how do we test whether we're slower?
The velocity, changing velocity, the variable velocity of light is the proof.
Okay.
And I told you what the digital velocity of light is, like, from the square root of 1 over the square root.
Right, because of the geometry.
The change of
Yep. Planck lengths and square roots underneath the one.
The thing is, we have in black holes, the new paradigm explained how the event horizon becomes an absolute barrier, how matter gets broken down, how light gets down to Planck's length and can't get any shorter, and matter gets broken down through what I call de Broglie radiation, which is like synchrotron radiation, where particles radiate all their energy before that slows down.
Cool.
But we can prove it through the variable velocity of light, and that's also evidenced, and that gets evidenced by what they think is the acceleration of the expansion of the universe. Henri Poincaré.
Yeah, Poincaré. Yeah,
He was he was one of the greatest mathematicians of all time, and he was a contemporary of Albert Einstein. He actually saw a model for the universe that is precisely what this universe is. And his model was that you can have both a universe that is finite, as seen from the outside, and infinite, as seen from within.
Neat.
And the way that it worked is, you start off with you assume the universe is a very hot center, and the edge is absolute zero. And you start off the center, and you march towards the edge. But as you march towards the edge, your temperature cools. But as your temperature goes down, you have a decline in all the physics of that internal universe change in proportion to the reduction in the temperature.
You mean physical laws change?
Physical laws change as you march towards the center.
So I thought that at the beginning all the laws were...
No, I'm just talking, he's doing a conceptual thing.
Oh, I see.
So he says, as you walk towards the center, your legs get shorter as the temperature drops. And such that as you get closer, and he says, okay, your radius is, let's say, big R. That's the radius of the sphere out to the end. And you're little r. And so what happens is, as you go towards the center, it's big R squared divided by little r squared. Well, what happens is, as you start to approach that whole point, what happens is it goes down to 1. So what happens is your temperature goes down and down by the combination of those squares.
Okay.
Well, the thing is, as you walk forward, your legs get shorter and shorter and shorter until
Why?
you never can reach, because all the physics changes in proportion to the distance from the center.
So your legs get shorter.
Your legs get shorter.
Okay.
Well, that's what he said. So what happens is you're marching, you never ever get to that level. It's the same thing. What he's really saying is the velocity of light gets slower and slower as you walk.
Oh, okay.
So the velocity of light, you never can get to that end because the velocity of light keeps getting slower.
So
he
according
described
to him,
this exact universe.
So according to him, the speed of light's variable as well, but according to him, it gets slower as time expands. Your theory says it gets faster.
No. Velocity of light gets slower as the universe expands. Remember, it was 10 to the 30th faster than it
it was faster at the beginning. Oh, my fault.
So the thing is, it was very hot and it gets faster. And we're going towards a colder and colder universe. It's something 2.76 degrees above absolute zero right now. If you just take the general temperature.
Kelvin.
Yeah, it was an extraordinary temperature at the beginning. And so what happens is our legs get shorter as we walk towards the ultimate goal, destiny. In time, it keeps getting bigger and bigger and bigger. So the thing is, you never can get to that end. So there would be an infinite progress to get to that point you never can get to, because your legs keep getting shorter until it's impossible to get there. He figured the universe out 120 years ago, and that's unbelievable when you think about it.
Yeah, and there was no concept of black holes at that point.
No concept.
Not
They
at
didn't even
all.
know the universe was expanding.
Nope.
The thing is, how can you have a universe that
I
contains
think they knew that the
So
universe was larger than the Milky Way galaxy yet.
Yeah, they barely knew what the Milky Way galaxy was.
Yeah.
But the thing is, that's what the basic concept of the universe, the idea of having containment. He saw you can have a universe that's from the outside is finite. A black hole in our universe looks finite to us, but to the inhabitants of the universe within that black hole, it's infinite. And the thing is, their time and our time don't relate. What happens at the surface of a black hole is there's a total separation of cause and effect between what goes on in the black hole and what goes on outside the black hole.
Well, you give me a lot to think about. I don't know that I understand all of it, but
Well, I covered an awful lot, and
Yeah.
the concepts are fairly deep. But the thing is, it's a very robust theory, and the formulas of general relativity confirm it all. And that's why the formulas are absolute. If you can prove one aspect of those formulas, it all links together. The velocity of light
it all follows from one. Gotcha.
It all, because I have 232 formulas, and they're all interlinked. And the thing is, you think, well, the universe is all probabilistic. It's probabilistic within that interlinkage of general relativity, but the general relativity is an absolute.
Yeah.
And that's what makes this such a wonderful situation, that we live in. So we can live with confidence that the universe is will develop as it should, because in the end it has a beginning, it has an end, and it has in between experience.
Excellent.
Thank you.
Yeah, thank you. Like I said, this is a lot to think about. I think I got about 70% of it, and I think I'll have to watch this video again. And if you need to watch the video again, that's great too. It'll be here on YouTube. And
I covered a lot.
Yeah.
And the thing is, it's hard to get one aspect of it without doing it. But
right. I know it's all interlinked. I know you have a lot of things, and we're going to do more conversations like this so that we can illustrate more points, and they all interlink. So far we've got the variable speed of light, and today we talked about time. So
But the nature of information is something we can look into too.
maybe that'll be our next video. Tune in then.
Thank you very much, guys.
Great to have you.